In this exercise, we're going to discuss a graphical fit of an FOPDT to temperature control lab data. We have our general equation for an FOPDT, and we're going to take into account the deviation variables of temperature and our heater setting deviating from, we'll say, 23 degrees is our normal steady state temperature, and 0 is our steady state heater setting. So we're going to first have the temperature just be 0. We're going to have, or I should say, our heater setting be 0 for 30 seconds. And then for the last 7.5 minutes, we're going to have it be at 70%. You've seen this code before. First, we have some code to get our Active Directory and save our CSV once we create it. I'm going to try to read that CSV first, and I've gone ahead and I've run our temperature control lab data already, and that's just so we can discuss what's actually going on. Then we close that, and then finally what I've done is I've just gone ahead and graphed that. We're going to go ahead and look at this picture, and we're going to discuss the dynamics of what's going on based on this graph of our data. And we'll go ahead and I'll just draw some lines as we go through this. So the first thing we're going to want to do when we identify a first order plus dead time graphically is where our input and our output and the times at which those happen. We know our input for our heater went from 0 to 70%. And we'll look at our input to output for our temperature control lab. And what I'll actually do is I'll come down, I just have this right here, this another cell, and I'll just say for our differential temperature, I'm going to make that equal to T1 underscore, that's my array that stores temperatures, and minus T1 underscore 1. So what's going to do is our DT is going to give us, and I'll say our DU, our change in input, is going to equal 70. So then our gain is going to equal to the change in output, DT, change in temperature, divided by DU, change in input, and we'll have that be output as well. The next thing we want to know is the time it takes to reach 63% of that. So we want to know, go ahead and we want to know what 63% of that is. So we're going to say time it takes to reach, let's say T, we want to know the temperature that we're going to use for our dead time. Or sorry, not our dead time, our process time constant. So I'll just go T process time is going to be equal to, and let me just move this over now that we're coding. T process time is going to be the time that our temperature is going to equal the first temperature, so T1 underscore 1 plus 0.63 times dt. That's about all I really want to do with our code. It just makes it easier to do without a calculator. Go ahead and I'll run that section. We can look at T1 underscore. I need to capitalize that T1. We'll run it one more time. So our change in temperature is 51 degrees. So our gain is going to be 0.7324. Now process time, T process time, that doesn't seem right to me. Plus, I did multiply, that should be a plus. Run it one more time so you can see that no one's ever really perfect at this. You just got to use some common sense. So first actually we're going to look at what our dead time is. So our dead time we have pretty consistent. It's actually losing a little bit of heat right here, relatively constant. We'll first note when the heater turns on at about 30 seconds. Then we'll look for an inflection point in the rising temperature. With that identified, we'll use the slope to create a line, and the difference between where that intersects with the original temperature and the starting point of that temperature is what our dead time will be. Our final step will be determining the process time. It will start with the end of our dead time, so at about 50 seconds, and will go until the temperature is equal to 56.8 degrees. Since that's what we determined before as the initial time, the initial temperature, plus 63% of the total temperature change. To do that, we'll just draw some lines here. We'll draw one for the end of the dead time, and the one the temperature that we're looking at, and then going down. We'll measure the difference between those two, and that will be our process time. And there you have how we'll fit graphically our FOPDT model to our temperature control lab. We first did a step test, and then we looked at the difference in dead time and the change in output per input. Then we used that to create the process time constant. If you have any questions or comments, feel free to leave them below.